Ever wondered where a word like quark actually comes from? One of those science terms.
Mm-hmm.
Or maybe how the universe's basic rules, which seem so simple, can create all the, well, stuff around us, all the complexity.
Yeah, it's a fundamental question, really.
Well, today we're diving deep into the mind of someone who thought about these things constantly. A real intellectual heavyweight, Murray Gell-Mann, Nobel Laureate.
Absolutely. His name might not be instantly familiar to everyone, maybe not like Einstein or Feynman, but his impact, huge.
Definitely. And for this deep dive, we've got some great material, 2 really extensive interviews with Gell-Mann himself.
That's right. One's from the Nobel Prize channel, the other from the Academy of Achievement. And they're not just, dry physics lectures.
No, not at all. They cover so much ground.
Yeah.
Physics, sure, but also language, complexity, environmentalism, even how we discover things.
It's a real tapestry of his thinking.
So our mission today, we want to pull out the key insights from this incredibly broad mind.
Mm-hmm.
How did his work on tiny particles lead him to think about the whole universe?
And how did his sort of relentless curiosity connect all these different fields?
Exactly. So get ready for some potential aha moments, because we're going to explore how a mind like Gell-Mann's saw the world. And where better to start than with that word?
Quark.
Quark. If you've heard of Gell-Mann, it's probably because of quarks. It just sounds right, doesn't it? But the origin, it's pretty unique.
It really is. Initially, he just liked the sound of something like quark.
Quark. Huh.
Yeah. And crucially, he liked that it didn't mean anything specific. He was wary of names that tried to be descriptive.
Why was that?
Well, think about proton. It means fundamental. But then, oops, we found out protons are made of smaller things. Quarks, in fact. So the name becomes obsolete or misleading.
Ah, I see. So he wanted a blank slate.
Pretty much. And then came the literary connection, serendipity strikes.
Right, the Finnegan's Wake part. This is wild.
He's just leafing through James Joyce's book, a notoriously difficult book.
Famously dense, yeah.
And he spots the line, 3 quarks for muster mark.
And that was it. That fixed the spelling.
That fixed the spelling. Q-U-A-R-K. Now what's funny is Joyce probably meant it to rhyme with mark, like bark or hark.
So not the sound Gell-Mann was using.
Not exactly, but Gell-Mann, ever the creative thinker, found a justification for his own pronunciation. He linked it to a barman character in the book, suggesting maybe it meant 3 quarts for muster mark.
Huh. That's clever. Like finding a post hoc rationalization.
Sort of, though, most Joyce scholars and dictionaries say the primary meaning is probably the cry of a seabird, a gull.
Okay, so the bird cry makes more sense in context, maybe.
Yeah.
But still, what a story.
And it gets better, the Oxford English Dictionary, the OED.
The authority on English words.
They actually consulted Gell-Mann directly about the word's origin for the dictionary entry.
No way.
Yep, it might be the only OED entry where the etymology is based on a private letter from the person who coined the word for a scientific concept.
That's incredible. A testament to his impact, really.
It is. But the quark story isn't just about the name. There's this whole issue around how his prediction was understood or misunderstood.
Ah, yes, the mathematical quarks issue. Let's unpack that.
So Gell-Mann's big idea, physics-wise, was that quarks would have fractional electric charges. Plus 2/3, minus 1/3.
Which was weird, right?
Yeah.
Everything known then had whole number charges, like +1 or made of 1.
Exactly. Revolutionary. And his initial thought, which turned out to be correct, was that these quarks would be permanently trapped inside bigger particles, like protons and neutrons.
Meaning you couldn't just find a lone quark floating around.
Precisely. You couldn't isolate one. So in that sense, he called them mathematical. Real, definitely real, but not directly observable on their own.
Okay, that makes sense. Real but confined. But that's not how people took it.
Well, no. History, or at least popular accounts, often twisted it. Made it sound like he thought they weren't really real, just a mathematical trick.
Oh, that must have driven him crazy.
He said it did. He spent years trying to correct the record, explaining it to authors, even the Nobel Foundation. He called it a strange perversion of a fact that makes its way into history.
Wow. You can see how the word mathematical could be misinterpreted by non-physicists, though. It sounds abstract.
It does, and it highlights a real challenge in science communication, doesn't it? How do you convey these really nuanced, complex ideas accurately?
Especially when they challenge existing assumptions.
Right. He was thrilled when the experimental evidence came in, confirming quarks inside protons and neutrons. The people who did that work got a Nobel for it. But yeah, that historical footnote about his mathematical comment clearly annoyed him.
Understandably. And maybe that frustration or just his way of thinking pushed him towards looking at the bigger picture, beyond just fundamental particles.
I think that's a fair connection to make. He definitely transitioned. He moved from focusing purely on the simple, fundamental laws of physics to exploring what he called plectics.
Plectics, okay, another Gell-Mann coinage.
Yep, plectics. He derived it from Greek and Latin roots common to words for both simple and complex.
Simple and complex. So what was he studying with plectics?
Essentially, the interplay between the two. How do the incredibly simple, fundamental laws of nature—
Like the laws governing electromagnetism or gravity?
exactly. How do those simple rules give rise to all the incredibly complex things we see? Evolution, ecosystems, human societies, galaxies, all of it.
It's the big question, isn't it? The ultimate, how did we get here?
Precisely. He wrestled with this paradox. The underlying laws seem universal, unchanging. Every electron is identical to every other electron, everywhere. That's the simple part.
Okay.
But the world isn't simple. It's full of individuality, adaptation, learning, history. That's the complex part. So where does all that richness and variation come from?
If the rules are the same for everything.
Right, and his answer involves chance, accidents, probabilities.
Okay. So it's not just deterministic clockwork unfolding.
No. He pointed out, first, quantum mechanics itself introduces inherent uncertainty. The fundamental laws aren't strictly deterministic at that level. And second, no observer can ever know everything about the initial start of the universe.
Right. You can't have perfect information.
So you can't perfectly predict the future. He liked this image of a branching tree of possibilities for the universe's history. He even connected it to a story by Borges, The Garden of Forking Paths.
I know that one. Infinite branching realities.
Kind of like that. He argued that the specific history we observe, our reality, is shaped by both the simple fundamental laws and what he called an inconceivably long sequence of accidents or chance events.
Accidents. Like the specific way a nebula collapsed to form our solar system, or a particular mutation.
Exactly, those kinds of things. Unique, unrepeatable events. But here's the crucial next step. Some of these accidents aren't just random noise. They create new conditions, new regularities that influence what happens next.
Okay, hang on. Accidents creating regularity. How does that work?
He called them frozen accidents. Think about the genetic code. Why is it this specific code mapping DNA codons to amino acids? It likely arose from a series of chance events early in life's history, but once it became established frozen, it created a stable regularity that all subsequent life built upon.
I see. So the accident becomes a new rule, almost. A historical contingency that shapes the future.
That's a great way to put it. It becomes a fixed point. So the universe's complexity isn't just randomness, it's layers of these frozen accidents built upon the fundamental laws.
And this relates to his idea of effective complexity.
Yes, he defined effective complexity as basically the length of a concise description of a thing's regularities. Not just the randomness, but the meaningful patterns.
So white noise has low effective complexity because its description is simple. Random. A perfectly repeating wallpaper pattern also has low complexity. Repeat this tile.
Exactly. But something like a living organism or a language has high effective complexity because you need a long description to capture all its meaningful, non-random patterns and rules its regularities, many of which arose from those frozen accidents.
That's a really powerful framework. It gives you a way to think about complexity across totally different fields. Biology, cosmology, even our own lives, maybe.
Absolutely. It makes you question any purely deterministic view. The universe seems fundamentally shaped by this interplay of law and chance.
And this way of thinking about how things develop through laws, chance, and emergent patterns, it seems like it connects directly to how he thought about creativity and scientific discovery itself.
It really does. He often talked about the creative process, citing the classic 4 stages that people like Helmholtz and Graham Wallis described way back.
Which are?
Saturation, you just immerse yourself, fill your head with the problem. Then incubation, you let it go, let your unconscious mind work on it.
The sleeping on it phase.
Right. Then illumination, bang, the aha moment, the insight breaks through. And finally, verification, you have to actually check if the brilliant idea works.
The pattern feels very familiar.
It is. And Gell-Mann was interested in how to maybe nudge that process along, how to break out of old ways of thinking, what he called basins of attraction.
Like getting stuck in a rut.
Exactly. He mentioned things like deliberately introducing random noise into your thinking. He cited Edward de Bono's quirky suggestion. If you're stuck on a problem, pick the last noun on the front page of the newspaper and try to connect it to your problem just to jolt your brain onto a new track.
Huh. That's definitely random. Did he ever experience that kind of sudden insight himself?
Oh, absolutely. He had a fantastic story about his work on strangeness.
Strangeness. Another great physics name. He coined that one too, didn't he? Facetiously.
He did. It was a quantum number for particles that behaved, well, strangely produced easily in strong interactions, but decaying slowly via weak interactions. Anyway, he was explaining an incorrect theory about it one day.
Okay.
And he made a slip of the tongue. He meant to say 5 halves for some value, but he accidentally said 1.
Just a verbal mistake.
Just a mistake. But in that instant, hearing himself say 1, he realized that was the correct answer for a different correct formulation of the theory. His unconscious mind had seemingly figured it out, and it slipped out accidentally.
Wow. That's incredible. Like his brain was ahead of his conscious thought.
It points to that deep incubation process, doesn't it? Another really formative moment for him about the core of science happened when he was just a grad student at MIT.
Okay.
He was at a seminar. Someone was presenting some theoretical approximate evidence suggesting a particular nucleus, boron-10, should have a spin of 1.
Standard academic stuff.
Right. Then from the audience, this guy Gell-Mann, described as a grubby man, just pipes up and says, "Hey, the spin ain't 1, they measured it."
Straight to the point. Experimental reality check.
Exactly. And for Gell-Mann, it was like a lightning bolt. He realized the goal of science isn't to impress your professors or spin elegant theories for their own sake. The goal is to agree with what this grubby man found in the laboratory.
Agreeing with nature. That's the main thing.
That's the main thing. It's about reality, not just intellectual games.
That's a great story. And that spirit breaking down barriers, focusing on the real connections, seems central to his work with the Santa Fe Institute, too.
Absolutely central. He was a huge advocate for breaking down the walls between disciplines: art, science, history, social science. He saw it all as part of a unified culture.
No artificial silos.
Right. And the Santa Fe Institute, which he helped organize, was designed precisely for that. To bring people together from totally different fields: physics, biology, economics, anthropology, computer science, to tackle complex problems, specifically complex adaptive systems.
Systems that learn and change, like ecosystems or economies.
Exactly. And he told this wonderful anecdote. There were 5 linguists, all from the same department at their home university. They came to Santa Fe, started talking to each other in this different interdisciplinary environment, and ended up having conversations and making connections they'd never made back home in their own department.
Wow. Just changing the context, the environment, unlock something new.
The structure of the place encouraged it. It really makes you think, doesn't it? How can we create more environments like that, personally or professionally, that spark those unexpected connections?
Yeah, how do we foster that kind of serendipity? It's crucial. And his wide-ranging interests didn't stop at abstract ideas. He was deeply concerned about the tangible world, particularly the environment.
Very much so. He had a real passion for preserving biological diversity. He focused especially on the tropics, recognizing that's where diversity is highest, but also where the threats, poverty, population pressure are most acute.
A critical situation.
Yeah.
And he had a practical idea for that too, right? The RAP?
Yes, the Rapid Assessment Program. He cooked up the idea with an ornithologist, Ted Parker, literally around a campfire in Venezuela.
That sounds like a Gell-Mann kind of origin story.
Doesn't it? The idea was driven by urgency. Instead of spending years doing exhaustive species cataloging in an area.
Which is the traditional scientific approach.
Right. But by the time you finish, Gell-Mann argued, the area might already be gone, deforested, developed, whatever.
So RAP was about speed.
Speed and expert judgment. Small teams of highly skilled field biologists go in, make a quick, approximate assessment of the area's biodiversity and conservation value. Get the essential information needed to make conservation decisions now, before it's too late.
Pragmatic. Sometimes an approximation now is better than perfect data too late.
That was exactly the philosophy. And his environmentalism also tied into his critique of economics.
How so?
He felt that standard economic calculations were often just caricatures of reality.
Caricatures. Strong word.
Because they systematically ignored or undervalued natural resources. Things like clean air, fresh water, forests, biodiversity.
Right.
They're often treated as free goods or externalities.
Meaning their cost isn't included in the price of things.
Right. Or if it is included, it's often approximated as zero.
Right.
Which is absurd, he argued. He spent decades fighting this, pushing for economists and policymakers to internalize these costs.
To actually account for the true value of nature and the true cost of depleting it.
Exactly. He believed our survival and the survival of countless other species literally depends on learning to do that. And interestingly, he pointed out it wasn't always about sacrifice.
What do you mean?
He noted that if you actually calculate correctly, removing market distortions, sometimes conservation makes economic sense. He said saving energy in many cases will make money, and reducing carbon dioxide emissions will, in some cases, make money rather than costing.
So smart environmental policy can actually be smart economic policy if we just stop using the caricature math.
That was his argument. And this wasn't a late-life conversion for him either. Go back to his Nobel Prize acceptance speech in 1969.
Wow, that far back.
Yep. He actually gave part of it in Swedish, and he used it to congratulate Sweden for proposing the very first UN conference on the environment, which happened in Stockholm in '72.
Yeah.
He spoke about the preciousness of our blue planet seen from space. He was consistent on this for decades.
That's impressive. A long-term commitment. It really prompts you to think about the true costs we overlook in our own spheres, doesn't it? What are the externalities we're ignoring?
It's a vital question, and looking at his own life journey is just as fascinating. You wouldn't necessarily guess Nobel Prize in physics from his childhood interests.
Oh, what did he want to be?
Archaeologist. And a linguist. He said he had absolutely no inclination to work on physics as a kid.
So how did he end up there?
His father. It was the Depression era, and his dad was understandably concerned about financial security, a reliable source of income.
Practical concerns.
Very. He pushed young Murray towards engineering, but Murray resisted. He apparently said, I'd rather starve, and besides, if I build anything, it would fall down.
Uh-huh. Self-aware, at least.
So his father pivoted. Okay, not engineering. How about physics? He sold it by promising that the advanced physics, things like relativity and quantum mechanics, would be really exciting.
And was it?
Gell-Mann said yes. His father's promise turned out to be absolutely true, so that nudge changed everything.
Yeah. Amazing. And his brother was a big influence, too.
Huge. His older brother, Ben, 9 years older. Ben introduced him to nature, bird watching. Apparently taught him to read using a sunshine cracker box.
The cracker box. That's brilliant.
And Ben really fostered this idea of a unified culture in him, that you didn't need these rigid boundaries between subjects. Art, science, history, it was all interconnected knowledge.
That view clearly stayed with him. What about his formal schooling?
He was apparently bored easily, so they skipped him ahead a few grades. He always preferred tackling advanced stuff over what he saw as dull classwork. He felt pretty strongly that education often failed kids, especially with uninspiring teachers.
Yeah, a bad teacher can really turn you off a subject.
He mentioned his wife Margaret's history teacher as an example. He believed students should be exposed to the latest stuff in science, not just century-old basics. Keep it exciting.
Makes sense.
Yeah.
Keep the curiosity alive.
Mm-hmm.
And despite his incredible intellect, he had this quite funny self-deprecating side, too.
Oh, yeah. He'd playfully call himself terribly lazy.
Lazy. Murray Gell-Mann.
Well, lazy in the sense that he felt he was always behind because he took on too many things. And he called reading a terrible addiction, even reading junk, from newspapers to, yes, cracker boxes again.
That's very relatable, actually. The feeling of being overwhelmed by interest. It makes him seem more human.
Totally. And he wasn't shy about having strong opinions on scientists' roles in society either. He took clear stances on some major controversies.
Like the Oppenheimer case.
Yes. He considered the campaign against Robert Oppenheimer, stripping his security clearance, a crime. He saw it as fundamentally a policy disagreement about nuclear weapons strategy, things like that being wrongly weaponized through the security system.
A misuse of power based on differing views.
That was his take. He also commented on Linus Pauling, another Nobel laureate who became a prominent peace activist.
Pauling campaigned heavily against nuclear testing.
Right. Gell-Mann acknowledged Pauling's concerns about the health risks from atmospheric tests were legitimate, but he felt Pauling sometimes exaggerated a lot of the data to make his case.
So he saw nuance there. Didn't fully agree with either side, perhaps?
Seems that way. He respected Pauling's impact, though, saying he deserved the Nobel Peace Prize he received. It wasn't about agreeing with every detail, but recognizing the significance of raising the issue.
Interesting distinction. And he got involved in the evolution versus creationism fight, too.
He did. He was instrumental in organizing and circulating a legal brief, an amicus curiae brief, for a Supreme Court case about teaching creationism in science classes.
What was the outcome?
The brief was signed by almost every living American Nobel laureate in the sciences. It was a powerful statement from the scientific community upholding evolution.
So he believed scientists should engage in public issues, but responsibly.
Exactly. His view was, don't just spout off opinions using your title as authority, especially outside your expertise. That's abusing the platform.
Right.
Instead, he advocated for scientists to join with colleagues from many, many other walks of life for serious discussions and serious research on important, complex societal problems, collaboration and careful study, not just pronouncements.
Yeah. It's a call for humility and engagement, isn't it? Makes you wonder, how important are that intellectual flexibility and humility for really understanding anything complex, science or otherwise?
I think his life suggests they're absolutely essential.
So we've really covered a lot of ground today, from the deep dive into quarks and their strange name,
To plectics and the dance between simple laws and complex reality.
through the nature of discovery, the Santa Fe Institute's interdisciplinary vision, his passionate environmentalism.
And his own life story, his views on science and society. It's quite a journey through one mind.
It really is.
Mhm.
Murray Gell-Mann's work truly embodies that quest to understand the simple and the complex. A relentless curiosity driving exploration across so many fields.
And always with that commitment to both scientific rigor and thinking about the broader societal implications.
Definitely. And maybe a final thought to leave you with, drawing on his ideas. Gell-Mann often stressed how our universe, everything we see, is co-determined by fundamental laws and that long sequence of accidents.
The simple rules and the frozen accidents shaping reality together.
Exactly. So considering that, how might understanding that interplay between the underlying principles and the chance events help you navigate the complexities in your own life, your career, your understanding of the world?
It's a powerful lens. What frozen accidents in your own past, big or small, have created new regularities, new paths that define who and where you are today.
Something to ponder.